In February, we had Frank Andrewartha give us a demonstration of an installation at a site way out in the country and start presenting information to us on things that weren't right, things that could be fixed, things that could be made better. Tonight, we're getting the second part of that journey. He's going to expand on the challenges that you encounter and the recent technologies that have been developed, especially by Frank's team, to challenge these. He's going to talk about his new asymmetrical waveguide system that he uses and give some examples of improved audio and clarity intelligibility. But he's also going to take us through the trip from inside your brain all the way out to the electrical signals going to the speaker and show where things can go right and where things can go wrong. I'd like you this evening to welcome Frank back and let him calm down after he's had a few issues with the technology. And welcome him to the AES. Bravo.
Thank you very much. And it's another reason why old people shouldn't be allowed near computers, really, isn't it? Now, this is continuing on the theme that of intelligibility in difficult acoustic environments, which is where we were the last sort of demonstration presentation. Now, unlike the first one, which went very conspicuously in one direction and went somewhere, and then we had a demo at the end, this is actually going to start at the end and work its way back to the beginning. And by this, I mean that we're going to start at where the sound ends, and we're going to work our way back to the sound source, and essentially we're look, I know that you've probably all sat through any quantity of hearing presentations about eardrums and the inner ear and the outer ear and why we're all going a bit deaf, but I do need to start at this point. And as much as I'm going to run down a few rabbit holes in this presentation, hopefully all the rabbit warrens will come out at the same place at the end. Now, the thing to bear in mind is what we have is a machine, and it's a machine that, although it's mass-produced, every sample is different. Now, that is attested by the fact that if we set a room full of people up and play some music, especially if you're at the Melbourne Hi-Fi Club or at any group of engineers who are going to be critical listening, they'll all have a different opinion. Now, that fact was not lost on this gentleman and his wife, Don and Carol Davis. Now, I'm sure everybody here at some point in time has run into his book, Sound System Engineering. Well, he actually has written quite a few books, and he was also involved in measurement systems. Now, I know we talked about measurement systems in the last presentation. Well, what Don did was, as you started to have the development of miniature microphones, he found a group of audio engineering students, and they created a little miniature piezo microphone that was small enough to mount on an eardrum. So, of course, he did that. He went and got a whole lot of students, and they mounted transducers on their eardrums, and he measured them all, did frequency sweeps. And they were also able to record exactly, play some music, stand in front of this loudspeaker, hit record, and actually hear and plot what everybody was actually hearing. So it turned out, of course, that everybody had a different frequency response. That's at the eardrum. Now, we're not talking about anything behind the eardrum yet, that's just at the eardrum. Now, as I mentioned last time about comb filtering and the hearing circuit and the delay between your two ears from sound hitting one side to the other, and the comb filtering at the processing part of the brain, and the comb filters giving you indications of location in space. Well, in our case, the head acts as a natural barrier between the two ears and thus a sound source at one side will produce more intense stimulus of the ear nearest to it, and incidentally the sound will also arrive sooner, obviously at the closest ear, thus helping to provide the mechanism for the localisation of sound based on intensity and of course the arrival times. You see, now for locating objects in space. Now of course, because of the shape of your ear, and this area outside here is called the pinna, remember that word, and of course one of the reasons it's shaped like this is so that you can locate high frequencies, and of course high frequencies behind you will not be as loud as high frequencies in front of you. And consequently, it's always amused me when people on a stage would have foldback monitors down here, when of course your ears are on the side of your head. So of course, obviously for foldback and for listening, you've got to have where the sound source is physically located has a lot to do with, of course, what it's going to sound like. So what we're going to do now is just have a little look on the other side of the eardrum. Now, I'm going to play this little this little video. Someone's gone to a lot of trouble to make this. It is actually pretty interesting, and when you see the actual mechanics behind the ear, it's quite extraordinary that we can even agree about anything at all when it comes to what something sounds like. So, let me just indulge this for a few minutes and.
The sense of hearing is accomplished by a process known as auditory transduction. The ear converts sound waves in the air into electrical impulses, which can be interpreted by the brain. As sound enters the ear, it passes through the external auditory canal, where it meets the tympanic membrane.
Anyway, you can see it's quite an extraordinary piece of work, and it gives you an appreciation for the people who came up with the cochlear implant, because when you look at the part where the conversion process into electrical impulses to the brain is obviously very, very small, and they've managed to, over the years, extend the frequency response that those implants are capable of, and to think that's been done with an Aussie company. You just wish you'd bought shares in that 25 years ago, and they're worth 20 cents each. But they've remained obviously leaders in the field. So quite fascinating. But the outer middle ear, there's a whole lot of little details that work in relation to airborne sound not being reflected out, and that there is an optimum impedance match. Because if it wasn't, a lot of these sounds would be reflected, and the first part of your ear is actually there to amplify sound, and the pinna, which is this part here, presents relatively a large surface area compared to the eardrum size, but of course it's relatively small compared to the size of our heads, where in the case of an animal like a dog will have much larger ears compared to the size of their heads, and consequently can hear a lot better. So obviously we hear well enough for what we have to do, but when you summate all of the parts of the ear, both the design of the pinna, these little ripples, the length of the ear canal, and the way it focuses, has a natural resonant frequency, which I'll get to in a sec. There's something like 30 dB of gain by the time it hits the eardrum, which is pretty extraordinary. Now, getting back to that listening through the pipe thing that Don Davis did, what we have here is another little graph where it's summating the individual effects of the outer ear and its effect on sound, because each one of them will tend to amplify at a different frequency. And the largest amplifying effect is actually the length of that canal, which has its largest effect at about 3K, is where it's really its resonant frequency is. So 3 to 4K is the area where it's most amplified naturally, and of course that's the area where we're quite sensitive. And the fact that it has a natural amplifying capability is, of course, means that that's likely to be the area we have the most hearing damage, or that's where it's going to settle in the quickest. So if you ever have the hearing test for your driver's license or something, 4 to 5K is the area you're likely to have the most damage. Now, so really when you look at it, we can pretty much settle the idea that any two people are going to hear the same thing, because they're pretty much not. They're not going to have the same polar pattern as far as their hearing is concerned. And this also suggests, as much as we went into measurement systems last time, that any measurement system is going to be not necessarily indicative of how people are going to hear, but as an engineering exercise, of course, you can't have a datum point without measurements. So obviously, regardless of whether you're using the Alcon or the STI or the clarity index, they're all going to be measuring for something different. But essentially, they're only going to give you a data set that you're going to have to use as a guide. So moving on to the venue, it's really this is where our problems are. It's really a question of how is your set of ears going to respond in that venue when a sound source is propagated. Now, if we have a look, last time we went in a little bit into this. Now, the modern venue is very different from the work of Polykaletos the Younger, and obviously this is a built environment that was designed to promote acoustic gain. Now, what we have really in this picture is a machine. And it looks like a venue, but it's actually a machine. And the way that's designed, the venue is the sound system. It is the amplifier. And of course, we can all marvel at the cleverness of how this was done. But of course, that area has a great deal of acoustic gain. And in our time now, putting a sound system in a venue, this is actually now going to work against us. And of course, the enemy in our modern venue is the masking influence of reverberation on speech. Now, we talked about this last time, and I also mentioned something about the effect of a phenomenon called critical distance. Now, if we look here very briefly, I'm sure you've all done this to death, but you've got your first reflection, it bouncing around the room, and then it breaking up into a multiplicity of reflections that effectively sound a little bit like white noise, and they'll have a masking effect on consonant sounds, and there goes your intelligibility. Now, if we look at this phenomenon of critical distance is really the point in a room where the listener position, the amount of energy that is coming from the reflective surfaces, is roughly equal to the energy they're receiving from the direct sound source. Now, by the time you're at critical distance, you've probably already lost a certain quantity of intelligibility, and it's surprising as you get older how critical distance seems to move closer to the stage. But anyway, that's it is technically something that you can measure. Now, in some cases, people try and make adjustments for lack of intelligibility by boosting equalisation and changing things around that way, but it's never terribly good. Now, looking at this whole point of, I can get this one to go. we have another little animation. You've seen all this sort of thing before. It's a wave propagating, hitting surfaces and bouncing off. Once again, you can see all your little nodes and antinodes. Now, it's sort of a nice animation, but it's not completely realistic because that's done at a frequency. And of course, we're hearing full range sounds. So the truth is actually way worse than that, because what you have is nodes and antinodes spread across the whole frequency spectrum. And of course, they're all going to differ depending on the wavelength. So with every venue, realistically, we're going to have some kind of intelligibility problem. And of course, the expectations of the audio system are going to vary with venue and also with what the purpose of the venue is. So I've split this up into two classifications. One is just your generic public spaces where you're going to be making background announcements, which of course are very important that they're heard properly. And then of course you have performance spaces where we have full range speech and music. I'll look at them separately. Let's take public spaces. Now, there's your railway stations and airports and what have you. And the main product you see in those environments is 100 volt line distributed speaker systems. Now, realistically, poor performance is the result when there's no expected test standard when a system has been installed. And in most cases, especially in the case of a distributed sound system, there really isn't an audio design. There's just someone's come along with a shotgun and blasted a whole lot of ceiling speakers everywhere, with the builder going for the cheapest thing, spending the minimum and having a cable puller basically put them in. And like any sound system, it's no pay, no play. So I don't know if you've ever tried to hear where your airplane is at Essendon, at Tullamarine Airport. Every time I go there, I hear and I can't, unless you're standing right underneath one, you can't understand it. So especially the Qantas area where all the departure lounges are is just abysmal. And I remember when that was actually put in, and they were tendering that, and believe me, they spent the least they could possibly spend, and they got what they paid for. Now, distributed systems don't actually have to be bad, even if they're using a cheap system. I think it was Joseph Stalin that said quantity can have a quality all of its own. So, you know, if you put enough of them in and absolutely carpet the place with them and power it with enough power, well, it'll probably work. But the question comes down, if you're doing a distributed system, how many should you put in and how should it be done? Now, I talked a bit last time about the Hasse effect, where I will go into a bit more about this later on when we're talking about delays. And the Hasse effect, one of the cornerstones of it is the ear's capability and the mind's capability of resolving echoes. And beneath a certain threshold, you don't hear an echo. Now, as your echo gets shorter and it becomes it starts to have interference and comb filtering, you start to get directional information about it. But basically, the ear is not a great determiner of distance when you're down to about 20 or 30 feet. So consequently, that tells you if you're putting in ceiling speakers, you don't really have to worry too much about echo. So in actual fact, a distributed system can work really well, and you can pretty much get rid of the whole problem of echoes just by putting in a stack of ceiling speakers. There's actually charts around that have you know, how the Hasse effects work and how masking reflections can be overcome, and there's a region that they refer to as a Hasse effect region. Now, when it really comes down to it, I mean, it says here 5 milliseconds. In actual fact, at 5 milliseconds, you can't hear that at all. So you can have programs. There's a program here by I think it's TEF do this one, KEF, sorry, where you can sit there and you can map it out, because obviously with ceiling speakers you've got a polar pattern, and so long as the area of that 3K sort of 4K harmonic information area, so long as that's not beaming too directionally and your speakers are high enough, you can actually get enough intersecting coverage. And of course at those frequencies your interference is minimal at those frequencies as well. So you can actually basically carpet a ceiling with speakers, so long as they're high enough and they're wide enough dispersion, you'll get away with that. So it's not that difficult a problem to resolve. They just have to do it properly. Now, when it comes to a full range sound system, that is much more difficult. Here we're talking about your houses of worship, multi-purpose venues, which are often quite difficult. Now, there's a wide range of audio solutions that will work, but like any solution, it has to be completely installed and imposed, not just some of it installed and imposed. Now, here's an example of a venue. Now, it's pretty much a bit of a nightmare, really, if you were to think about putting a sound system in there. What would you do? Well, for a start, there's going to be people getting upset about sight lines. There's going to be all sorts of headaches in a building like that. Now, you don't just have, the reverberation is not so much the problem in that kind of building. The problem is just coverage. Now, if you hang some speakers above that stage area, sure, you can't put in anything too big because the architect's going to get upset. You've got all these balconies that are going to be shaded, and of course the coverage is going to be very, very non-uniform. So you look at we look at the reverb situation. I mean, we talked about RT60 last time, and the time that it takes a signal to drop by 60 dB in a building, and the reflections collapsing into a sort of a reverberant swoosh. Now, in handling the reverberant field, we look once again at the inverse square law and the common denominator to the intelligibility issue, which is too much energy bouncing around in the wrong place. Now, in the ceiling speaker situation, a large number of ceiling speakers was close to the listener, so the problem of critical distance reflections and multiple arrivals is not an issue. In a performance venue, the model is completely different. The point source situation is going to basically throw sound all over the place, but it can still be controlled, and what the difference can be is adding little fill speakers. Now, in the case of what is a delayed system, we run into the problem, say you take a situation here where we have a large sound system throwing out into a distance, losing energy over distance, and of course in this situation here what we have is a bunch of delay speakers. That's been a common solution especially for OH&S, where you don't want it so loud at the front that you're going to damage people's hearing, but you want a uniform coverage up the back, but you don't want it to go 2 kilometres up the road. Now, they don't have to be big sound systems to use satellite speakers on delay. Now, here we have the Port Fairy Folk Festival. This is in a hocka. Now, your problem there, once again, the ceiling isn't that high. You can't really hang a PA, so in that environment they have to use a ground stack. You run the risk of it being super loud in front of the stage, and of course at a folk festival, it's not a Metallica concert, they don't want it that loud, they want it to sound natural. So in this room what we had was two concentric rings of delay. So there'd be a first delay, and then further up the room there would be a second delay. Now, the trick there is how do you make that natural, and how do you avoid the problem of reflections and echoes, and how do you time these delays? Now, we're back to the point of sound travelling at 1150 feet per second, which works out roughly at 1 foot per second. So if we look at our inverse square law and we look at how much acoustic energy we're going to drop, a lot of this can be quite arbitrary, but you start off at how loud is it going to be at 1 metre in front of the sound system at the maximum level you want to run that sound system at. Calculate the amount of dB drop you're going to have, and then just prior to the point where it's going to fall off, or alternatively you're going to be hitting critical distance, that's where your delay speakers go. Now, in the case of a lot of venues, if you have like a long shoebox room with a low ceiling, you might actually have 2 or in some cases 3 rows of delay speakers. Now, the real trick is, of course, how to mesh that all in together, because, as I said, the ear doesn't really detect a 30 millisecond delay as an echo. From 30 milliseconds on, it'll maybe start to have a resolution problem. And if you have speakers over your head, you're going to have that first arrival is going to be the speaker above you. And we're going to talk about precedence effect. And what's going to happen is the first sound that hits you is where the image is going to come from. Now, it may not be a delay, but it will be an image shift. So the performer could be a mile down, could be, say, 50 feet or 40 feet that way. But the sound's coming from here. And these will be little speakers. So they'll be a bit like this. And then you've got the wave following. So what the Hasse effect is about is actually precedence. It's about moving the image around. It also can, with delays and precedence effect, and its effect on phase relationships, it can also be used for steering. When you talk about lobe steering of sound systems, that's also part of that too. Now, Helmut has completed a study in 1951 describing a bunch of experiments of how people perceived delay signals and echoes. In his experiments, he had a group of speakers placed in various locations, and by varying delays and having somebody sit in the middle, he could basically have that image moving around the room. That was also in the early days when they were starting to experiment with stereo imaging. And basically how it worked was somewhere between 5 and 35 milliseconds, the listener perceived a shift in the acoustic image. Basically, the shift was in the direction of the first wave to arrive. And even when the delayed signal was at a reasonable level, the image would still be at the first arrival point. Now, once the delayed speaker became to about 10 dB, say 8 to 10 dB, in other words, twice the perceived loudness, over the level of the first arrival, then the image started to move again. So what that tells you is that if you're going to create a viable delayed system, you have to bear in mind that you have to have this smooth transition. You have to have your primary arrival coming essentially from the most forward system, and you're limited to how loud you can turn up your delays. So consequently, what you end up with is more delays over the distance monitoring very closely what their actual level is. Anyway, that's basically essentially the precedence effect. Now, on how to set delay times, remember we had that room with all the shadings. Now, how someone would deal with that? You'd have a primary system, and in fact even a little line array or something would have hung nicely between those two, that sort of proscenium arrangement. And what you'd have to do in that kind of is have multiple delay rings. Now, the other problem that you run into when you're setting delays, especially when they're being mounted on walls or pillars, is in most cases your delay speaker is going to have to point slightly tangentially across the progressing front wave. Now, in theory, that's not a good thing, but in reality, because the people in the coverage area, due to the tangential nature of that wave, are going to hear, they're not all going to be in the same time plane. So it gets, once again, in timing your delays, having more of them, turning them down, largely solves that problem, because you've really got a 20 to 25 millisecond window that you can play with. The other thing that can be done with it is, in the case of, actually, the next one, is quite often in an arrayed sound system, you will have to have fill speakers. You might have something at the front of a stage in a large environment. You also may have some downfill speakers that are covering the closest seats, and then of course you have your primary system. Now, ideally, that all needs to be timed, because this is of course where you can have cone filtering problems. You can have reflections, and all sorts of little weird things can start happening with the sound. The quickie way to do this is to actually run pink noise through the system and walk around the room. I found that for measurement purposes, sometimes your ears can be the best measurement. So you run a bit of pink noise, and the same thing goes when you're running delays. You just switch it all on, put on the pink noise, and walk around the room. And it's quite surprising how you'll be walking along and it'll be just the same sound, and then you'll hit a spot where you'll have quite a noticeable change in the tone, and that's where you start playing with your delays. Now, if you've got rough measurements over a distance, you'll have a pretty good idea of what those delays are going to need to be. The other thing is, of course, is if you are having a comb filter problem, for instance, if you were having something from this little downfill speaker, you'll be surprised by turning them down even just 3 or 4 dB, which is hardly noticeable to the people at the ground. That's quite a different energy level actually at the loudspeaker. So those situations, plus playing around with your delay times, can make a terrific difference. Now, when we take this kind of room, here's your conventional old style town hall. Now, unlike the Greek theatre or some of the other early venues that had a purpose in their acoustical design, these were never good. There was never one of these made in the history of the world that had anything going for it acoustically whatsoever. So if you ever were to have a job where you had to specify or do something in one of these places, and of course now they want to restore them all, and you try and tell me an architect or a conservationist who will let you hang delay speakers in that kind of venue, and of course it's not going to happen, and quite rightfully so, because it's going to look completely out of context. So we're back then to the problem of how do you deal with that, and then of course a lot of places will turn around and hang a line array, which once again are quite large, will look out of context, will hit that back wall, and just, we're back to our critical distance problems and all these other things. Now, this was where our asymmetrical system came in. And intelligibility is not made with an EQ, it's not made with an audio processor, it's not made with plugins or corrective technology. It actually comes from addressing the sound source, and the problem source is acoustic energy in the wrong time and place. Now, we had this earlier last time with the effect of putting two loudspeakers together in an array. Now, a lot of those big rooms, those big empty boxes, same thing in some of the cathedrals, were handled by hanging a central cluster. And that actually worked pretty well, and really is a very viable way to do it. But the problem is these days is people they think they want stereo. They want to see a speaker either side of the stage, and as soon as you do that, you are reflecting more off walls, more off ceilings. It just turns into a problem. Now, this was our lobing effect of a two-box array of a conventional point source system, and as we could see, that would actually be audible. Now, this environment here, once again, we have a three-box array, which theoretically should be worse, but for anybody that was at our test out in the burbs, we had a two-box array in a reverberant space, and you couldn't hear a lobe anywhere. And as you walked up the room, there was no problem with critical distance, and the image seemed to be with you around the room. Now, that's actually quite hard to achieve with a conventional system, in the same way that if you hang a line array system, you're just going to send a whole lot of reflections around the room when it hits the back wall. Now, what I didn't really talk about last time was how asymmetrical distribution in the vocal range is actually achieved. And realistically, you could say, you walked around that room, you actually had pretty uniform coverage, and yet there was no lobing. Now, theoretically, that's defying pretty much what we'd imagine as the laws of physics. So, and the other thing you'd say is, well, if that's such a good idea, why doesn't everybody do it? Well, there are a lot of challenges in designing an asymmetrical system. Horn drivers are... There's a bit in a horn driver. They require a lot of favourable geometry for the wave to transition into the horn flare. And realistically, horn drivers have not changed much since the early phase plug designs, really after the Second World War. There was a patent, I think it was Western Electric actually did it, and they had and their patent was called a maximum modal suppression phase plug. It applied a whole lot of mathematical analysis to the motion of a curved diaphragm and a method for calculating width and position of slots used in the phase plug. It was building on a lot of long-established technology, but this patented design significantly reduced the occurrences of unwanted resonances in the cavity between the diaphragm and the phase plug. The result of it was greater modal suppression and reduced what they call air non-linearity. I think really what they mean is a shock wave, actually. The benefit was a much better time domain response and much lower distortion than had existed previously. And of course, here we have a picture of a good old Altec driver, complete with cutaways. Now, there's a few variations on how phase plugs are made. If you've ever pulled one apart, there's some that have axial slots, there's others that have like a pepper box, and there's some that are a combination of all of the above. And of course, their mission is to basically time it so a vibration emanating from the diaphragm uniformly arrives at the end of the at the driver where it's going to match onto the horn. Because obviously if they all arrive in different time domains, we're going to have a phase shift problem and tangential waves and non-linearity. Now, what I'm going to show you here is when a diaphragm is moving, it's not a straight up and down motion. What's happening is there's all of these resonances that take place in a diaphragm. And the larger the diaphragm, the more of them there will be. And where those resonances are depends on the size of the diaphragm, the composition of the diaphragm, the stresses on it. And obviously for a diaphragm to be efficient, it needs to be thin. It needs to be very stiff in order to not resonate. It needs to be made of lightweight materials. Most commonly it's titanium, beryllium, or in some cases they'll be polymer material. But the real question of the selection of the materials is how sound is going to travel through them. Because if you could imagine a wave rippling through a pond, it starts at one point and the energy radiates through the pond. Now, in a compression driver, where you have a voice coil, we just see the whole thing moving like this. That's not actually what's happening. Is the electrical energy is being converted into mechanical energy, and that is around the edges of the diaphragm, and that starts to move first. And then that motion is then transmitted through the material substances and then converges in the centre. So consequently, you will get a little lag from the moment that the motion of the driver starts to the moment when the motion at the centre of the driver starts. There's actually a whole lot of mathematics. It's a mathematical study of vibration modes, of the nature of how energy is transmitted through solid substances. Large diaphragm drivers operating off wide frequency ranges are actually the most prone to it. To little breakups and tangential waves, and one bit of it's going this way and another bit's going this way, and you get all this kind of stuff going on. Now, the higher the frequency, the modal behaviour that occurs at very high frequencies is going to be different to the behaviour at the lower frequencies. In a normal compression driver, a smaller compression driver like a 1-inch horn, you can typically have problems around 7K, where you can have quite a lot of elasticity taking place, and the material will have be very naturally resonant at those sort of 6, 7, 8K frequencies. And you'll notice in some horn drivers, when you measure them, you'll see these little zippy peaks. Well, that's really where that's coming from. And there's a whole lot of mathematics they do, and they refer to as elastic modulus. There's the elastic modulus, there's the tensile modulus, and a number that measures an object or substance's resistance to being deformed elastically. Elasticity being a non-permanent deformation when a force is applied to it. So basically we can see that diaphragms need to be stiff and light. They're a moving mass, but they're not a uniform moving mass, and they'll have all these ripples like a drum. So their behaviour is really more like a drum skin than it is as a solid plate. And the modal behaviour causes local variations that produce sound within the diaphragm that is actually not being initiated in the first place. So here we have our cross-section of some phase plugs. Now, if you imagine the diaphragm curving over the top of this, and we have our diaphragm and the combination of the waves we wanted plus the little tangential waves that are rippling off the surface. Now they've got to bend around all these corners and make their way out the phase plug and hopefully arrive at the end of the driver to match the horn in all of the same plane. Now, as they're bending around the driver, we have accelerated, think of this as fluid dynamics. The air is like a fluid, and we're accelerating this fluid around a corner. Now, there was a thing you might have heard of Bernoulli's law. He's the guy that came up with a whole stack of formulas about acceleration of fluid and pressure. That is, acceleration down a confined channel goes up, the pressure on the sides of the channel goes down. Now, without it's his calculations that we come up with the carburetor in a car, for instance. There's also a lot of Bernoulli's theorems are applied to do with aircraft lift, even though that's actually not quite how an aircraft flies at all, but it's very commonly cited. And the behaviour of air is treated as a fluid, as the laws of fluid dynamics apply to it. But once you get to about, I think it's about point Mach 3, it ceases to behave as an uncompressible substance and becomes a compressible. It starts becoming uncompressible. So it becomes progressively more uncompressible as it is accelerated. So of course, what happens is as the sound wave is bending around these points, we have it accelerating and then slowing down. So we're having pressure changes. So then the air, as we start getting to higher and higher SPL, starts forming shock waves in these channels. Now, there is an acoustician's name for it, which I just can't think of quite what that is, but it's something that you'll notice with horn drivers. Quite often at a lower level they sound pretty good, and then as you start pushing higher sound pressure level into them, you suddenly start getting peaks, and more particularly you start getting some dips, which is really in a lot of cases what the peaks are. And that's effectively the shock waves building up in the phase plug. So what we did was we had to... Your problem with developing an asymmetrical horn flare comes down to things like path lengths. In a conventional horn, yes, you've got variations in path lengths from the centre to the outside. The distances all become different. That becomes way worse when you're talking about an asymmetrical flare. So in order to get something relatively linear out of an asymmetrical flare, and this is why a lot of people haven't done it. This has been tried. Altec tried it back in the 50s. But on a conventional compression driver, it's very hard to get it to work. So what we looked at doing was we had to come up with basically the world's most linear compression driver in order to make it work on an asymmetrical flare. Now, what we have, in the end, we didn't build this, somebody else did, but fortunately for us, it works particularly well on our system. And we have what you could call a maximum modal suppression phase plug design. It sounds like something you put in a sales advertising campaign. But anyway, applying mathematical... this is coming from the company. Applying mathematical analysis to the motion of a curved diaphragm, the engineers developed a new method for calculating the width and position of the slots used in the phase plug. This patented design significantly reduces the occurrence of unwanted resonances in the cavity between the diaphragm and the phase plug itself. The result was greater modal suppression and reduced nonlinearity, in other words, shock waves. which is really what this is about. It's about cutting down the shock waves. The benefit is a better time domain response. Now, I don't know what a time domain response is. Maybe someone else can enlighten me what that is. But effectively, it's a much lower distortion than the existing industry standard. Incorporated into the design is the phase plug design. Now, drawing that more deeply makes it stiffer. The problem is, and the reason why people didn't do that before, is it actually makes it much harder to make a phase plug, because the more concave the dome, the more involved you've got to get with your flat phase plug path link. So theoretically, drawing a very deep diaphragm makes it more difficult. Now, thanks to 3D printing now, that isn't such a problem anymore, because you can now make phase plugs that are mathematically correct. Whereas previously you could have made one, but if you're trying to mass produce something and sell it for a reasonable price, well, obviously you've got to have something you can churn out. Now, if you take your conventional axial type phase plug designs, they kind of work, but they're made to be easily mass produced. So essentially, having that deep drawn design effectively moves the breakup problem from that sort of 7K range, and we actually don't really start having it fall apart till you get to about 17K. Well, fortunately in the PA business, 17K, nobody worries about getting that high up, so it gets back to a principle that we've found is if you can't solve a problem, camouflage it or make it go somewhere else. Put it somewhere where nobody's going to notice it. So then, of course, we're back down to the question of impedance matching. Now, acoustic impedance is simply the product of the transmission of sound through the medium, through the density of that medium. You know, you bang on a steel rail, the sound travels much faster through a steel rail than it does through air. So air is not particularly dense, and it's a relatively low impedance medium, whereas a steel rail or water is a much higher impedance, and consequently when those impedances are not matched, sound wave will bounce off water. If you're inside a swimming pool and someone's playing music outside, you're not going to hear it because it's basically just going to bounce off. There's a huge impedance mismatch. Now, remember I was talking about earlier in air, how air is technically, it's a compressible medium, but it's not a compressible medium. And once you get to a certain velocity, when it's contacting a hard surface, it becomes not compressible. So bear in mind we have a sliding scale here. So if you have, you're trying to get too much air down a pipe too quickly, it starts acting like a solid. So consequently in the mouth of the horn, if you're pushing too much energy into it, you're going to start having the impedance effectively change. Now, if we have a look at how it moves through the horn, essentially we have our very high pressure area in the diaphragm. It's arriving at the mouth of the horn, hopefully in a coherent manner. It's going to progress up the horn from a high pressure to a low pressure area. Now, what you're not seeing in this is, of course, we have another impedance coupling transfer taking place, energy transfer, which is actually at the mouth of the horn. Now, if you can imagine the air at the mouth of the horn as an invisible diaphragm. So really what we've got going on here is a lot of levers. We're going from a very high energy environment with a lot of with a very small amount of movement of air to a low energy environment with a very large movement of air at the front. And of course this is how the horn is acquiring its efficiency. But to get that to work and to have that in a uniform sound spectrum, we need to have a transition of that impedance in a manner where it's not going to send waves bouncing back down the horn again. So effectively, impedance matching the horn is really an important function, and the ideal horn driver would be designed with the horn. You would actually have the horn you just essentially have your horn driver, and you continue. The maths of that design would continue across the horn. Now, when we were talking about the little resonances in diaphragms, we found, along with a lot of other people probably found the same thing, that the way that diaphragm is made, including the alloys that are in it, and the crystalline grain structure within that thin sheet, have a lot to do with its behaviour and how it's going to resonate. We found that if you're using an aluminium diaphragm, if you add 2% of platinum into that alloy, it totally changes its behaviour. The way it will resonate, the frequency response, the whole thing will change. Now, you could turn around and say, well, how do you find that out? How do you in the case of a cone-driven speaker, you can sit there with a Klippel analyzer and you can derive a tremendous amount of data in terms of how that diaphragm's behaving. But how do you do that in a compression driver? Well, there's actually a method that's been around for a long time. It's called the waterfall plot. Now, I think that Don Davis, who we saw early, was one of the guys who was behind this. I think the first time I saw one of these was actually on a TEF analyzer. But what we have here, this is a three-dimensional plot. Now, if you can imagine our two-dimensional plot being the very end, you see, you get a plot of a horn driver, and you get a two-dimensional picture, and that's it. It doesn't really tell you much. It tells you there's a whole lot of dips and peaks there. But some of those dips and peaks you could make go away with an audio processor. Some of them you could. But there are some things there that are actually the reason that that dip or peak is there. And the three-dimensional plot tells you pretty much everything, because every one of those tails is a resonant point in those drivers, because that is a time, energy, frequency plot. So it's actually telling you over time, because the time constant is coming back this way. So in designing horn drivers, that machine is your best friend. And basically we found that if you sit there and you change the alloys, you change the shape of the driver, the diaphragm, that is your guide. Bearing in mind that most of what we see has been designed to be mass-produced, to be made easily. And most people copy everyone else. Nobody wants to really be too original, because originality doesn't sell. What sells is something that's a bit original but really looks like something you've already got. So consequently, we did a lot of work with waterfall plots when we were developing the flares. Now, audio processing has come a long way, but it really can't make reverb go away. It can't stop a resonant diaphragm from resonating. It can't remove reflections from a ceiling. It can't stop slapback, but it can make a certain quantity of compensation caused by a phase plug or in a horn circuit, but it's basically limited to camouflage. As previous, as I said earlier, this sounded like a bunch of snake oil. But the question comes down to, can we move all the problems around rather than solve them? And effectively, that's what we've done with this kind of design. And when we talk about the 3-box array or the 2-box array, where we should really have all these tangential waves, the fact that this horn system has been developed. Essentially, we've taken the horn driver. Once we had the patented system with which we could see was delivering us the potentially flattest response. The trick then was to design this driver, design the horn around the driver. Unfortunately now, there's a whole lot of, well, not a lot, there's a couple of programs that you can really sit there and model this out. So, back to the point of energy control, we ended up with the system that you heard last time was a 30 at the top, 60 at the bottom of the flare. We put most of the vocal range into that flare so that the element of intelligibility was going to be achieved by having the maximum coherence in those frequencies that our ear naturally uses to hear speech with, knowing that the area of the most trouble was around the 3K, 2 to 3K, 3.5, 4K. They were the real trouble zones. So consequently, when we modelled all this, we did it in a way to confine, because when you're designing a horn flare, the wider the dispersion, the harder it is to make that uniform. So by making it narrow, 60 degrees at the bottom, 30 at the top, when you start to array them, and of course here we have the idea of trying to have sound away from the walls and ceilings, focusing the energy and moving the critical distance. As I said, other people have tried this idea. This was Nexo, built a very popular product, but they never thought of using it as a room intelligibility killer. They built these as a foldback monitor. It's a fantastic foldback monitor, but to get that to work, they had to use a lot of processing, and it works as a foldback system. But as soon as you try to array that, it all falls apart because the dispersion of it is too wide. But it was essentially, they came out with that 15 years ago, and we looked at it and thought that was still the cleverest. They were the smartest guys in the room when it came to designing horn flares at that time. Yet they weren't the smartest guys in the room when they thought of application, because they thought, oh, we will make the finest foldback wedge in the world, and they did. But the problem is they had a terrific idea and then just let the whole thing go nowhere. So here's another one. This is Harry up in Queensland, Audio Technologies. He's built his own version of that. Once again, it's in a foldback wedge, but they don't work in a room. The whole point of us coming up with a solution where the tangential component of a 2-box or 3-box array would be made less obvious meant that you could put them up in practically any kind of configuration and they would work. That's an environment in a church where the priest would walk out in front of the PA with a lapel mic. Now, that's normally horrendous. He would put the lapel mic under his cassock and he would speak with the thickest Indian accent you've ever heard in your entire life, and that church is in Traralgon. Now, lovely man, but you could just imagine a church in Traralgon full of middle-aged and older people with an Indian gentleman with a fairly thick accent. Of course, they couldn't understand him. So, of course, he contacted the local television repairman and said, can you get us a sound system? So he rang up Radio Parts, which is where you go for this sort of thing, and Radio Parts sold him this. And so then, of course, I got the phone call one day and he said, oh, how do you put these up? So I went down there and took a box of bits and showed them how to bolt it onto the wall and put it up, and it was amazing. It actually was stunning. The guy could walk in front of it and it didn't feed back, and they all got paid and it was all fabulous. So the whole point is, it's no point having a functional solution if it's not functional. I mean, you've got to make it so that pretty much anybody can plug it up and use it. This was another one. This was a Korean church, a 3-box array. Now, most array systems, you can only put the array up one way. Well, of course, you'll notice the spacing here is different. So the way we make our array hardware is so that you can actually independently point the boxes where they need to go for coverage. Now, this would have a little bit of a lobe because they're right next to each other, but this one there's virtually no lobe at all. So it's like when we walked around at the other church. Because the lobe is only limited to the bottom of the flare, what it effectively does, it comes up like a little spots. It's not a continuous energy node or antinode. It's just little nodes and antinodes that are spots around the room, and you actually can't hear it. Here's another alternative. This is using the same type of system. This is a combination of a delay here and a little primary centre cluster of 2 boxes there. Now, strangely enough, standing at the back here, you can hear that as clear as you like. The only reason they put the delays in is because it's a multi-purpose venue largely used by amateurs, and they just wanted to moderate the level at the front so they could just have more uniform coverage. Consequently, that is actually quite tangential, the way that comes across, but once again, they just you switch it on and you don't really notice it. Thing is, they could have actually used 8-inch. They could have used very small boxes to have done that, but the guy who sold it to them didn't understand all that, so he just sold them the most expensive thing he could, and off they went. They were very happy with it. Now, the other point of these systems is lightweight. Now, that's one guy holding the array while this other guy's, there's another church, putting it together with Bunnings chain. Now, I've got to tell you, I'm not a great fan of Bunnings chain, especially when it comes to PAs. And the only thing scarier about the Bunnings chain is that I happen to know on the other side of that ceiling tile it's a piece of wood holding the PA up. So the other thing is that with most architectured environments, the way they design it, you can't hang the PA anywhere, and where you can hang it, it's in the wrong place. So the other element of this design is these only weigh 16 kilos. Now, they'll take 600 watts RMS continuous power, so they're very powerful boxes. But there's no point in it weighing 200 kilos because you're not going to be able to hang it where it needs to go. So consequently, part of the practicality of the solution was to make it light. And as I said, the part of the solution was also to have a simple rigging system that if you've got an Allen key, you can put it together and you can hang the boxes and off you go. So despite all the potential for comb filtering and lobing and dead areas, as you heard in the demo, there wasn't really a dead seat in the building, and the image was uniform and consistent in the vocal range. Now, had I put that all up and measured it, you know, when we'd measure these things in the chamber, they didn't look too flash at all. They look all over the place. But when you actually take it out to the venue and you plug it in and you listen to it, it sounds terrific. So this gets back to that point of measurement systems are really good for getting paid if you're installing a sound system at a railway station. They're really, when we look at what we have available to us these days, there's any quantity of tools in the toolbox. Even with all of the dud venues that we have foisted on us for installing sound systems, there is actually enough. With all of the brands of stuff, with all the technology we've got, there is actually enough. There is really no reason why there should be a bad sounding venue. The key is understanding the tools and being able to get them to work. And, you know, the answer really is that one size does not fit all, as much as we have some solutions. you get back to that point of the distributed system. This distributed system should work when they're appropriately used. A line array should work perfectly if it's in the right environment. A line array with delays should work if it's what's called for. It all gets back to what's called for. And what's really called for is people who know what they're doing, specifying these. And hence I'm very pleased to see that the AES is still with us, and I see organisations like the SAE out here, and I think that, well, really, these young guys go out and start pushing black boxes around the job, or imagining themselves in the band room of some high-powered band surrounded by supermodels. But at some point of time, that party, if it ever arrives at all, which is pretty unlikely, is going to end. And so consequently what we want is young people fired up with enthusiasm and imagination to continue their studies and advance their knowledge, and ultimately be the people who take over from us and use all these fabulous tools and bring us to the new world that we so rightfully should eventually inhabit. And with that, I'll say thank you for having me, and I'll leave it at that. Is there any questions that anyone would like to ask on delays or horn flares?
Is there an upper limit to the size of installation where you'd run a 3 array?
No, there is that. I've found that works up to about 1,200 people. We're about to build a bigger one, but I don't actually think the bigger one's going to be any better for doing that job. The bigger one will be made for a different purpose. But that idea, I'd like to see. Our market is really up to the 1,200 people venue. We're really little box builders. And we don't try and sell speaker boxes, we try and sell solutions. And we make a lot of things that aren't around. We don't just want to make something because someone else makes one, because what's the point of that? It's already here. We try to work from the problem back to the product. And when I look at rooms over 1,200 people, there's plenty of solutions that work. They don't need any clever ideas from us. So I must say, of the solutions that do work, I still think that treating the sound as an energy distribution problem, that there's still some legs in that. And I think that steering and asymmetrical coverage has still got there's still more life in it if someone wants to do it. Yeah.
Yes. Some of the factors that you consider from having a centre cluster or side clusters, how do you make those decisions?
Well, I think it gets back to what's the purpose of the venue. Now, if you look at that, there's one with the little 3 boxes hanging in the centre of a 60s, late 50s built church. That's in Darwin. That's the Anglican Cathedral. Now, you think about an Anglican cathedral, they're not going to have a rock band in there. It's going to be a fairly traditional environment. And what they want is very clear vocals. And if someone's going to get up and sing, they want, they want it to sound. Someone's going to play an acoustic instrument, it has to sound like an acoustic instrument. Now, it's in a horrendous brick and concrete and glass building that's going to just destroy everything. You see, now, the guys that put that in were, there's a Darwin company called Audio Technologies who are really sharp. They do a lot of work outside of Australia, and they said that's the best sounding church they've ever done, and it's the worst church they've ever done for the acoustics. And that was the cheapest PA they've ever installed. And the only thing they were complaining about was they didn't charge more money, because it actually worked better than what they thought it would. Now, that was the perfect venue for that PA. That's exactly what it was designed to do, and we designed it to do that because people were complaining that there wasn't anything around that would do that. So that really was the target when we first developed that system. And it just gets back to the horses for the courses. What's going to work? And as I said, with that venue, that horrendous looking thing with the big sort of, proscenium thing at the back, they'd want a fat checkbook to fix that one, because you'd have to have 3 to 4 delay rings. You'd be on 2 levels of delays. You'd have the primary system wouldn't have to be that big. It would be virtually a delayed distributed system of high fidelity short throw boxes, but they'd all need to be able to handle a bit of power, because sometimes in those venues you'll need a bit of dynamic range. And the biggest problem in that room would be, how do you handle the bass? That would be hard. But it really just gets back to having the toolbox.
Question. I'm not familiar, Frank, with this product. Is it self-powered or?
No, it's just a passive box.
Just
passive box. Yeah.
Okay, so
We've stayed with passive. I mean, we do build powered systems, but in an installation, people look. There's a lot of fashion that goes on, and I'd rather go down with the ship of not following fashion, if the ship I think is going in the right direction. And in a venue, do you want to have to climb up there and get a box 30 feet in the air that's over seats if the amplifier in it stops working? Now, ours tend to not break down because they're so overbuilt that to take that box out, we pushed 3,000 watts into one of those for 3 or 4 hours. And the only reason we ended up switching it off was it was my business partner's Mardi Gras CD. And after a while, we just couldn't stand it anymore. You can only listen to "I Will Survive" so many times.
Good answer. Thank you.
You just don't break them. And so that's the point. You just overbuild it.
Yeah.
And if something goes wrong, it's in the amp room.
Sure.
Now, having said that, we are working on a system where you can stand down here and just with your phone turn it up and down and make changes and things.
But that master control would be co-located with the amps, you mean?
No, we're making one where you can actually have it in the box.
In the box.
But that's once again there's a purpose, there's a reason for doing that.
Right.
For your average installation of any brand, of any product, I'd stick with passive boxes. Or not passive, non-amplified boxes, and keep the amps in the control room.
Yeah.
The only advantage that you have with powered boxes in an array is you can turn individual ones up and down, and I have had occasions when that's been quite handy to do. Look, the powered system potentially gives you more options, but it's more of a hassle to install. You've got to have power and everything up there, and in some venues it's just not practical.
Yeah,
that's all I'd say.
Yeah. Difficult access.
So, just like your comments about, say, an EAW system that has like 20 loudspeakers with DSP, because what they're saying is, they're saying, well, this one speaker, I'll put this up and it can be a monitor loudspeaker, it can do vocal, it can do rock concerts with the same, you just turn on and make it into a line array or near field.
Look, I would...
How do you feel about that kind of...
Look, it's a bona fide approach. I would call it the engineered solution, because an engineer would love it. It's if I wanted to do something really complicated, that's what I'd be doing. But no doubt it works. If you want to, it's when I hear people say, "Oh, it's an elegant solution." You see, to me, ideally, an elegant solution is a simple one. But something like that, sure, it works, and there'd be applications where you could sit there and go and do it. But I've found that we've had a lot of, we're not EAW. We just have little, we do, most of our stuff we make is exported, but what we do is we go and fix problems. So when I look at the cost of that, and that's very flexible and it does a whole bunch of stuff and it fixes a whole lot of problems, you don't have to go. Anybody with a spanner and a Bunnings chain can put that up and it'll work. It requires almost no skill to get a result. And most of our markets are in third world countries or the Middle East, And believe me, I get asked some of the dumbest questions that you could imagine, but that's fine. I can live with that. And realistically, in the days when I used to do a lot of work with Nexo, who I thought were the technological leaders of everybody, held more patents than everyone put together, but couldn't sell the last lifeboat on the Titanic when it came to their actual way they address their market. But technologists, they're fabulous. Now, the thing is, it got back to that point of expensive, required technical expertise to use. When done properly, unbelievable, just stunning. But half the time it'll be awful. And the longer you leave it in the venue, the more sticky fingers go near those processors, the performance will decline accordingly. Whereas with these, there is no processor. It's just an amplifier. You just plug it in and switch it on and off it goes. And that gets back to the point of the thing I call white man think, which is, I've got a problem, so I'll come up with this elegant solution to the problem, you see. And that didn't quite work, so here's another one. And it's like you get the digital consoles with plugins, and they've got every plugin except a taste and talent plugin now. And the trouble is that it's just not fixing the problem. I just feel like saying, go home and practice your instrument. That microphone is not a substitute for technique. Please, just learn to sing. And I can't fix that. There's no sing in tune button here. If you're Kylie Minogue and I'm being paid enough, we'll make it work. But you're not. And realistically, that's why we put so much effort into the working on the drivers, and trying to make it so it sounds good to start off with, and then you can touch it up with a processor, because really you do need some processing basically to protect the PA from the users. And a lot of venues now, when you've got running delays and you've got other stuff going on, you might have zones and things. A processor is a great thing, and I figure if you've got a great thing, you use it. But essentially, you don't have to. I think you cannot use a processor as a substitute to fix a physical problem. Anyway, that's right.
I just want to know some comments about Australian manufacturing. Basically, when I went to China, I see so many knockoffs of this kind of product in 8-inch, 10-inch. In fact, it's hard to know whether it's genuine or it's a copy or whatever. So how do you deal with that kind of industry, this industry, and trying to make this an Australian product?
It is, but look, I found I could pick a Chinese copy of a Nexo box because the Chinese copy looked better. But when you got the screwdriver out, what was in it was rubbish. Now, and they didn't sound, they sounded horrible as well. Look, realistically, what I've found with Australian manufacturing, we're getting a bit of a run at the moment. And I turn up somewhere and you think, well, Australia, who knows about Australia in the audio business? Well, there's the Thielen small parameters, and it just goes on. We've way punched out of our weight in the audio industry. And you go to America and they go, oh, Aussies, do you know Bruce Jackson? Something like that. So, in actual fact, we hit a lot harder than we think we do. But it gets back to, think about it. If someone's confronted with a confusion, what do? They go with what they know. You walk into that restaurant where, those restaurants where a piece of steak's about this big and it costs about $400 or something, and they've got a menu that goes like this. In the end, you order the veal parmigiana because you just can't decide. You go with what you know. And this gets back to the brand build component. Now, in our market, where we've kind of done okay is we're getting known for engineered solutions. We're not trying to be, people come up and they say, a lot of companies will have a 6-inch, an 8-inch, a 12-inch, 10-inch, a 12-inch, a 15-inch, and this is our range for this market here, and then we've got this range here. And you walk in, it's more formula than a pop song. It's just, they've sat there and they've said, well, my distributors are demanded, and I feel like saying, well, mate, do you go to the dentist and tell him what tooth to pull out, we're the engineers, we're fixing their problem. If they want to come and solve their own problem and just buy some rubbish because someone else has got one, well, fine, that's all right. That's not our market. You really get back to this point of brand building, getting known for something, being reasonably original, because if you're too original, people get scared. So you've got to, if anything, you've got to hide your originality a bit and look like familiar, but be original enough that you've got the engineering credibility. And that's the thing. Engineering cred is really what it's at for our market, I think.
Well, there you go. That's pretty good. Any more questions? Okay, Frank, thank you again.
My great pleasure.
You've taken us from inside the head to inside the venue and all the bits in between. Excellent. Probably lots of discussion afterwards, but I'd like you to thank Frank for coming along and presenting for us tonight as well.
That's great.
Thank you. Thank you very much. Oh, thank you. Thank you very much.